Laying concrete masonry units and other bricks would have the similar procedures when estimated. The area or size of the wall would have to be determined and compared with the size of each block. Do not forget that besides those exposed above the natural grade line, there are embedded portions of walls and partitions too. Learn more about masonry works here in quantity surveying. From construction materials and testing, the standard dimensions of commercial hollow blocks have been discussed as 16 inches or 0.4 meters length by 8 inches height, or that is 0.20 meters. The only thing changing is the thickness of CHB, which ranges from 4 inches, 5, 6, or even 8 inches, the choice of which depends on the function of the wall or partition. When masonry units are laid on the ground, they would need to have some footing. Such footing is similar with structural foundations, but it would be shallower as it would only carry a floor's wall. The embedment of the wall footing is placed per layer, and as a standard, embedment of CHB ranges from 2 to 3 layers underneath the natural grade line. So what are the different ways in estimating CHB? There are actually two ways: the fundamental unit method and area method. The first method can be used by simply working on the logic of finding how many layers of CHB are required, and this is multiplied by how many units placed in each layer. The area method, on the other hand, uses a factor of 12.5 of CHB per square meter. Now let's derive how the factor of 12.5 came to be used for the number of CHB. If we have a 1 meter by 1 meter area of wall, and knowing that the width and length of each unit are 0.20 meters height by 0.4 meters length, we can lay around 12.5 pieces of CHB to fill a 1 meter by 1 meter area. Let's take an example to estimate units of CHB. A wall of 5 meters length and 3 meters height is to be estimated. Additional 2 layers are embedded under the ground. Solving this in fundamental unit method, we determine the number of layers and the number of pieces in each layer. Let's start with the horizontal layers. The computation takes the height of the wall divided by the height of individual CHB, or that is 3 meters divided by 0.2 meters, and don't forget to add the 2 layers embedded under the ground. And the result is 17 layers. Now for the number of pieces in each layer, divide the length of 5 meters with the length of each CHB, which is 0.4 meters, giving 12.5 pieces per layer. The number of CHB is the product of the horizontal and vertical layers. So that's 17 by 12.5, which is 212.5 pieces for the wall. For the area method, the number of CHB is taken as the area of the wall multiplied by the factor 12.5 pieces per square meter. So that is 5 by 3 plus 0.4, and this is multiplied by 12.5, and the result is 212.5 pieces. The mortar, which is a mix of sand and cement, will make the hollow unit solid. The two functions of mortar are for block laying or when we glue CHB on top of each other, and the other function is to fill the hollow cells within CHB. There are instances that mortar filler includes some gravel along with cement and sand. When estimating for mortar filler, the hollow cells should be analyzed. With the standard height and length of CHB, the length of each cell is also standard at 3 inches. The height is also standard at 8 inches. The only dimension varying is the thickness of the cell, and in order to get the proper dimension, just remember that the thickness of the CHB walls will always be an inch. Thereby, the thickness of each cell will be computed as the thickness of CHB less 2 inches. Add to your computation that in every CHB unit, there are 4 cells. The mixture for the mortar is also similar with that of concrete works. The table below shows the proportions of sand to a bag of cement, and it also varies from Class A of 1:2 to Class D, which combines 5 parts of sand to a bag of cement. Estimating mortar also comes in 2 methods. The fundamental unit method considers the standard thickness of mortar for block laying at 0.0125 meters. The procedure would start by taking the volume of mortar for block laying on each layer multiplied by the number of layers. The mortar filler will also be similar where one should determine the volume of mortar required to fill the cells. After learning all of the volumes required, check factors for cement and sand from the table shown earlier. Area method is the other solution in computing for mortar proportions, and this method would use the table shown for estimating. The factors provided will be used with the specific size of CHB used and the area is required. From the previous example we had in determining the number of CHB, let's continue with computing for the proportions of sand and cement for the mortar. Starting off with the fundamental unit method, we would have to divide the procedure for block laying and filler. When block laying, the standard thickness of the paste is 0.0125 meters, and from our computed number of layers earlier, we had 17 layers. The volume required, therefore, is measured as 17 layers multiplied by the volume of the mortar, which is 0.0125 thick, by 6 inches CHB, assuming we are working on a wall. And this is multiplied with 5 meters, the length of the wall, giving us the volume of 0.16 cubic meters. The mortar filler would also be computed as 4 cells in each CHB, and there are estimated 212.5 of them for the wall. This is multiplied by 0.1 from 6 inches less 2 inches thick of the cell by 0.075 meters width of the cell with 0.2 meters height. And that will come out to be 1.275 cubic meters. From both computations, the resulting required volume of mortar for the wall is 0.16 plus 1.275, or that is 1.44 cubic meters. Assuming we use Class B mixture, that will entail 12 bags of cement per cubic meter required, so cement is the required volume 1.44 cubic meters by 12, and that is 17.28 bags of 40 kilogram cement. Sand requires 1 cubic meter per volume, so sand is computed as the volume, which is 1.44 cubic meters of river sand. For the area method, all one has to do is to look for the area, and that is 5 meters by 3.4, giving us 17 cubic meters. Using the table, we take mixture B, and we multiply the volume. So for cement, we have 17 cubic meters by 1.013, giving 17.221 bags of cement. Sand will be the volume of 17 cubic meters with 0.0844 to give 1.44 cubic meters of river sand. Lastly, to finish the wall, one needs plaster. The proportions of cement and sand for plastering is provided in the table, where it will again be categorized on different mixtures from Class A to Class D. Take note that for plastering, fine sand is preferred over river sand. If we continue solving the previous example with plastering, check that the specification is for both faces requiring to be plastered. So that would double the area needing the work, and that is twice of 5 by 3 meters, giving us 30 square meters. With Class B, cement will then be multiplied by 0.288 for 40 kilogram bag of cement, and that would turn us 8.64 or around 9 bags of cement. Sand will be multiplied by 0.016, resulting to 0.48 or 0.5 cubic meters of fine sand.